Alright, so I'm just going to go through these slides real fast. We're talking about reaction mechanisms, and mechanisms are essentially a step-by-step process by which a reaction takes place. We can know the rate law for the overall reaction by getting data, but we can't just look at a reaction and know the rate law for that reaction. However, when we break it down into steps, you can actually figure out or deduce the rate law for the individual steps in the mechanism. Most reactions do not occur in a single step. They usually have multiple steps. You'll see 2 or 3 most of the time, and putting those steps together is going to give you the overall reaction. So look at this example. You have the reaction up here, all right? And then you have 2 steps that are a proposed mechanism. It's a series of steps to get that overall reaction to take place. Each step is called an elementary step, and an elementary step can't be broken down any further. So what you see is what you get. In order for a mechanism, as in order for the series of steps to be considered valid, the 2 or more, each elementary step together, they have to add up to equal the overall reaction. So if you look at this one, you have hydroiodic acid here. They appear on both sides. And then you have 2 hydrochloric acids and 2 ICLs, a hydrogen and an iodine. And that matches the overall reaction that we had up here. An intermediate is essentially what I just crossed out. The hydroiodic acid does not appear in the overall reaction up here, and so that is what is called an intermediate. There are different types of elementary steps, and they're characterized by their molecularity. So a unimolecular step has just one molecule, and then typically it's going to, it has to decompose. It'll split into products. Bimolecular, when you have those types of steps, one of 2 things can happen. Either you have a molecule that reacts with itself, or you have a molecule reacting with another molecule. Termolecular is in having 3 things. That can happen, but it's so rare because 3 molecules colliding with the right orientation at the same time is just very small, so it does not happen often, and we don't have to worry about it in our class. So, like I said, with deducing the rate laws, you can't know the rate law of an overall equation, but you can deduce the rate law for an elementary step. Because each elementary step happens due to the collision of the reactant particles, the rate is going to be proportional to the product of the concentration of each of those particles. As an example, I have the 2 bimolecular situations from 2 slides ago. And in this case, the first one, you have molecule A reacting with molecule B. Well, because that step is just involving those 2 chemicals, the rate law for the step, the elementary step, would be equal to the rate constant times the concentrations of each of those reactants. Down here, you have 2 of the same molecule, so that means the rate depends on that molecule doubly or second order, okay? So this rate would be second order with respect to A because there's 2 A's reacting. This one's first order with respect to each because there's 1 of each. So you can deduce the rate law of the elementary step. Remember, this is not the overall reaction. You can't do this for an overall reaction, but for each elementary step, you can do it that way. The rate determining step is the slowest one. So you're only as fast as your weakest link. So in this little example over here, you have 2 toll booths. No matter what, in area 3 over here, the cars are only going to be able to go as fast as the slowest toll booth. So let's say you have a slow checker here and a slow checker here. Well, as long as A up here and B down here are going at the same slow rate, the cars are still going to come through in part 3, and part 3 at the same rate. Doesn't matter how fast this person is or how fast this person is. They are limited by the slow people. Same thing is true in a reaction. The reaction can only proceed as fast as its slowest step, and that is called the rate determining step. So we're looking at this reaction. You have nitrogen dioxide and carbon monoxide coming together to make nitrogen monoxide and carbon dioxide. You find that the rate law for this equation is right here. Now, how did you find that? Well, you looked at the data. It had to be determined experimentally. So you had something like your nitrogen monoxide, your carbon dioxide. Those would be concentrations. And then you had your rate. So I'm going to make up fake numbers for the sake of it. You had 1, and then you doubled the concentration, and you held it constant. You had 1, you held it the same, and then you doubled it. And you notice this is NO2, by the way. You notice when you doubled the NO2 concentration, this quadrupled. But then when you doubled the CO2 concentration, not CO2, man, I really messed this up, didn't I? This is just carbon monoxide. When you doubled the carbon monoxide concentration, it stayed the same. So in other words, it's 0 order with respect to carbon monoxide and second order with respect to nitrogen dioxide. So you got this rate as is shown. That's all from the data. Now, to figure out a mechanism, you have to find a mechanism that will explain why carbon monoxide does not affect the overall rate. In this case, they have 2 steps, a slow one and a fast one. The first one involves only nitrogen dioxide. The second one involves carbon monoxide. First thing you got to check for is that the mechanism adds up to equal the overall reaction. Well, you have your nitrogen trioxides, they cancel. One of the nitrogen dioxides cancel. And what you're left with is equal to the overall reaction, so that's good. Now you have to look at the rate law. Well, the rate determining step tells the rate law for the whole reaction. The slow step, the slow rate, is the rate for the whole reaction. Well, in this case, if we were to deduce the rate law for each of these, the rate law of the slow step would be equal to NO2 times NO2, okay, rate. Down here, rate would equal a constant times NO3 times carbon monoxide. Well, in this case, this rate actually matches the overall equation, so we know that that one has to be the slow step because its rate is the rate of the overall reaction. So the 2 conditions for a mechanism to be valid are 1, the elementary steps have to add up to equal the overall reaction, and 2, the rate law that's predicted by the mechanism has to be consistent experimentally with the observed rate. So whatever you find the rate law to be experimentally, that has to match up with the mechanism. In other words, the rate law for the slow step must be equivalent to the rate law of the overall reaction. Now you'll notice a mechanism can't be proven. It can only be valid or invalid. So it's possible to get a mechanism wrong, but you're not going to be able to know for certain which one is necessarily correct. So when you're doing problems, just because your friend got a different one than you doesn't necessarily mean that either of you are wrong. You have to look at these criteria and determine which one is valid or if it meets those criteria. So I will talk more about the rest of this in a later video, but hopefully that's enough to